Hello students, I am Raghunanda working as an assistant professor of physics. So today we are going to learn about the law of conservation of energy and concept of work and energy, which is one of the subtopic from the chapter momentum and energy. So as we all know, the nature manifests itself into two forms, that is energy and matter. Matter, it is made up of material particles such as atoms and molecules, and energy, it appears in different forms, and all the activities of the universe going on because of energy. Now what is energy? Energy is capacity to do work, and it is a scalar quantity. The SI unit of energy is joules and its CGS unit is erg. The dimensional formula of energy is given by m L to the power 3 and T to the power of minus 3. So as we all know, energy will be available in different forms. The different forms of energy are mechanical energy, chemical energy, light energy, heat energy, sound energy, nuclear energy, electrical energy, etc. So, energy will be obtained in different forms. So, these are all some of the forms of the energy. Now, when we come to the mechanical energy, this mechanical energy is again divided into two types, kinetic energy and potential energy. Now, what is kinetic energy? It is the energy possessed by the objects by virtue of their motion. So, the energy possessed by the objects by virtue of their motion is known as kinetic energy. So, it is given by the formula half mv square. Whereas potential energy is the energy possessed by the object by virtue of its position or configuration. So potential energy is the energy which is stored because of its position or configuration. Say for example, here in this picture you can see that there is a person standing on this wall. So from ground, this is at some height, isn't it? Hence, the ball which is in his or her hand is having some potential energy. When this ball is thrown downwards, this potential energy will get converted into kinetic energy, and this potential energy is called as gravitational potential energy. So, due to the change in position from ground level to some height is known as gravitational potential energy, and it is given by mgh. Now let us know what is the principle of conservation of energy. The statement of principle of conservation of energy says that the sum of all kinds of energies in an isolated system remains constant at all times. So the sum of all kinds of energy in an isolated system remains constant at all times. Means the total energy of an isolated system remains constant forever. Means in another way we can say that energy is neither can be created nor can be destroyed, but it can be transformed from one form to another form. In case of mechanical energy, how this law of conservation of energy is defined? So it is defined as the sum of kinetic and potential energies at any point remains constant throughout the motion. It does not depend upon time. This is known as law of conservation of mechanical energy. So for that we need to consider one example here, example of a simple pendulum. So if we consider an oscillation of the simple pendulum, here you can see that at two extreme ends the potential energy is maximum. All the energy is equal to, that is the total energy is equal to the potential energy, whereas in the equilibrium position all the energy of the pendulum is only the kinetic energy. In between The energy is the combination of potential energy as well as kinetic energy. But when we calculate the total amount of energy at each position, it would remain constant. So that is the principle of conservation of energy. Now, after knowing the principle of conservation of energy, let us know some of the points related to work or work done. So, what is work done? When we say that work is done on a system or an object, so when force acts on an object, the object will get displaced in the direction of the force. Then we can say that the work is done by the force, and its SI unit is given by joule. So both work and energies have the same units, and work is expressed as the product of force and displacement. So this is true in the case when the force and the displacement are in the same direction. But in some of the cases, the displacement will be in the different direction and the applied force will be in the different direction. So at that time, the general expression for work is given by the formula W is equal to F dot R. Here R is the displacement, F is the force that is applied, which is equal to F into R into cos theta. That is, it is the scalar product of force and displacement. Now, here this will be the theta will be the angle between the force and the direction of displacement, and F cos theta is the component of the force along the direction of displacement. So we can give the general equation or general expression for the work done as the scalar product of force and displacement. Now, work done by a variable force. If different amount of force is applied, what will be the expression? Let us see. So assume that a particle is moved from point A to point B through a distance or through a path C. So at that time, how to obtain an expression for the work done? So for that, we need to consider 2 points P and P dash, which are very near to each other. Let the position vector of the point P be R, and let the position vector of point P dash be R plus delta R. Hence, the distance between P and P dash at this time is given by delta R. Now, here this is the direction of force at this point P, and these dotted lines indicates the line, or this is the tangent drawn to the curve at this point, and which makes an angle theta with the direction of applied force. Now, if dW is the work done in moving the particle from P to P dash, so it is a very small distance, hence we can consider it as a straight line. So the general equation is F dot dr. But in order to calculate the total work done from point A to point B, what we need to do? We have to take the integral of this. So at that time, what will be the expression of work done we get? So it is the integral between the limits A and B. That is integration of F dot dr between the limits A and B, which is equal to F cos theta into dr between the limits A and B. So this is the expression for the work done by a variable force. So after knowing about the expression for work done by a constant force and a variable force, let us know what is the work energy principle statement, or what is work energy theorem states. So the statement of work energy principle says that work done by a force in displacing a body is equal to change in its kinetic energy. So as we all know, when work is done on the object, it will get displaced, isn't it? So its velocity changes. Hence its kinetic energy also changes. This change in the kinetic energy is equal to the work done by the force on it. So this is the statement of the work energy principle or work energy theorem. Now let us prove it. So for that, let us consider a force F be applied to the particle in a direction opposite to that of its motion. So assume that a particle is moving and in the opposite direction a force F is applied. So what happens at that time? The particle will get slow down and comes to rest, isn't it? So then the work done by the particle against the applied force is given by W is equal to negative integral of F dot dr. Why we have used negative sign here? Because the force is applied in the direction opposite to that of the direction of motion of the particle. So according to Newton's second law of motion, we can say that force is the rate of change of momentum. So hence it is given by F is equal to m into dv by dt, where m is the mass of the particle. Now from these two equations we can write that W is equal to minus m into integral of dv by dt into dr. Now displacing the or what do you call displacing the positions of dv and dr. So what we are going to get? Minus m dr by dt into dv. But dr by dt is nothing but the velocity. Here the force is applied against the direction of motion of the object. Hence and it comes to rest. So the body comes to rest after the application of the force. It slows down and comes to rest. Hence we have to take the velocity to be going from v to 0. Hence it is given as half mv square. Means this energy or this work done is equal to the kinetic energy of the particle. So kinetic energy is the energy of the moving particle whose velocity is v, and when the force is applied in the opposite direction of its motion to stop it, then that amount of work done will be equal to the kinetic energy, which is given by half mv square. Now dot multiplying both the sides of equation 1. What is equation 1? So this is equation 1. Dot multiplying this equation by v. So what we are going to get? F dot v is equal to m into dv by dt dot v. So what is F dot v here? It is the dot product of force and velocity, which is nothing but the power. Power is given by dw by dt, that is rate of change of work. Hence this equation becomes dw by dt is equal to d by dt of half mv square. Next, let the initial velocities of the particle be u and final velocity be v. Then by integrating the equation 3, so which is equation 3, by integrating this equation 3, so what we are going to get? So dw by dt is w, which is equal to, so the time is 0 to t d by dt of half mv square into dt. So this is equal to, here dt get cancelled, so it is d of half mv square, whose integration will be equal to half of mv square between the limits u and v. When we solve this, we are going to get it to be is equal to half mv square minus half mu square. But what is half mv square? It is the final kinetic energy, and half mu square is the initial kinetic energy of the object. Hence W is equal to delta K, that is change in kinetic energy. The work done is equal to kinetic energy. So what is that statement of work energy principle states? So when the force is applied on an object, when it displaces, there will be a change in the kinetic energy, and then the work done will be equal to the change in kinetic energy of the particle. So this is the principle which we have proved. So in this lesson, in this session, what we have learned? We have learned what is an energy and what is the law of conservation of energy statement, and we have also learned we have also derived the expression for work done in the case of both constant force as well as in the variable force, and we have also proved the work energy principle or work energy theorem. Thank you.